the notes for AP Calculus on the topic of parametric formulas without the graphing calculator. So, remember with parametric formulas we've got another variable besides x and y, usually t, and that oftentimes represents time. And we're looking at two different components of the position in terms of time. So, when we want the derivative dy dx, we have to take dy dt divided by dx dt. Okay, so we'll have both of them, take the derivative each one separately, and then divide them. And you can see why this works mathematically, because when you divide by dx dt, that's the same as multiplying by the reciprocal, or the rule for fractions, which is dt over dx. And you can see then the dt's would reduce out, leaving you with dy dx. So that's how you find the derivative, which still represents the slope of the tangent line for parametric equations. The second derivative is a little bit trickier. So the way the second derivative works is you find the derivative of the first derivative, like you normally would, but then you have to divide by dx dt. That's the thing that may not be super obvious why that's necessary. So let's see why that is. So when you take the derivative here, is the second derivative, but here's what's different. These are different variables. They're not both dx or both dt, so you wouldn't write it as dx squared or dt squared. You'd have like dt and dx, both of them. And that's not the expression we want. Remember, our second derivative we'd write as this expression is the way it's commonly written. And that's not what this is yet. So, again, you can see why this would work though. By dividing by dx dt, just like we did here, that's like multiplying by the reciprocal dt over dx. So again, you can see the dt's would reduce out, and then leave you with two dx's on the denominator, which you usually write as dx squared without the parentheses like that. So that's how that works for the second derivative. You find the root of the first derivative with respect to t, because it'll be in terms of t on these parametric ones, and then divide by dx dt. Now speed's a little bit different here. Previously when we looked at speed, remember speed is never negative, it's defined as the absolute value of velocity. But without parametric ones, we were just looking at things moving in one direction, like an x-axis or y-axis, just one direction. But with parametric ones, you move to two dimensions. You've got two different components of the velocity. So you can see how this works most easily, I think, by just looking at a little diagram there. So let's say we had dy dt represents the vertical velocity. So let's say it was moving up, and dx dt is the horizontal velocity. Moving left or right, moving right. So if the particle, this is the horizontal component of velocity, dx dt, and this is the vertical component of velocity, which is dy dt. But speed, we want to incorporate both of those to see how fast it's really moving. Because really, if this is the horizontal component of velocity, and this is the vertical component of velocity, then the speed vector actually looks, because it has two components to it, like this. It's actually moving in that direction. It's just we're splitting it up into its two different components. Horizontal velocity and vertical velocity. So the speed formula, notice, just comes from the Pythagorean theorem. Because if you want to solve for speed, you'd have dx dt squared. Because you notice this forms a right triangle here. Plus dy dt squared. That's the vertical component of velocity. And you can see that would equal the speed squared. and then all you have to do to solve for speed is take the square root of both sides. And so that's where this comes into play, the square root of dx dt squared plus dy dt squared. Now notice, this formula is involved if there's a specific time you're looking at, t equals a. Then you'd have to substitute in that time into both the horizontal component of velocity dx dt and into the vertical component of velocity to get the exact speed. And remember with derivatives, there's two different notations. So in parametric ones, we use both ways. One is the rate of change notation like this, dx dt dy dt. The other one is x prime of t, y prime of t, in which case you substitute in a, it would look like this. Either way, it's the same thing. All right, so that moves us to distance. Remember, distance, or sometimes it's referred to as total distance, means the same thing. Traveled on some interval from A to B. Remember, we did this with regular velocity. When something was moving just one direction, it was the integral from A to B of speed, the absolute value of velocity. And in a sense, the formula hasn't changed because we still are integrating on the interval speed. Notice that's what this is right here. Just like we showed right here with the Pythagorean theorem, this is the speed, the square root of dx dt squared, or you can write x prime of t squared plus y prime of t squared. So we're still integrating speed, it's just the speed formula looks a little different because it's got two components for parametric equations, and it's still integrated from A to B. So it's the same idea, it's just a little more complicated because now things are moving in two dimensions instead of just one dimension. And then there's a couple things called vectors, okay? So vectors have more than one component to them. So previously we just had one velocity function, and that was it, right? It just told you where it was moving on the x-axis or y-axis or some straight path here. But now it's got two components, a horizontal and vertical component. So again, we're looking at one specific time, time A. You write it, it kind of looks like greater than or less than signs, but use these symbols here that are open a lot further than less than and greater than signs than inequality signs. That's how you write vectors, and with a comma separate them. So the x component goes first and the y component goes second, or the rate of notation dx dt and then dy dt. And again, it's just showing you if you plug in a specific timing. So and in the same way, since velocity has two components, this is the horizontal component of velocity, this is the vertical component of velocity. Acceleration is the same thing. It has a horizontal component to it, horizontal acceleration, and vertical acceleration. Okay. So there's two components. It's written the same way. It's just now it's the second derivative of each of them separately. Notice that's different here than the second derivative here, d squared y dx squared. That's really telling you, just like it would normally tell you, just like dy dx is the slope of the tangent line, this would tell you the concavity of the graph. The second derivative right there, concave up or concave down. Versus these are isolated into just horizontal and vertical components, not putting them together, looking at them separately. All right, so today we're looking at how we can find some different things with these parametric problems without the graphic calculator. All right, so the first example here says for time greater than or equal to 0, and that's, or in this case greater than 0, we're usually looking for non-negative times. The position of a particle is given by the parametric equations. So let me just move this down a little bit. There we go. X equals t cubed plus 1 and y equals natural log of t. So you want to find dy dx in terms of t. So we're not plugging in a specific time there. So remember, the form we saw, the derivative dy dx equal to, notice y is on the numerator, so it's dy dt divided by dx dt. So we need to find both of those. Notice here they are written just in x equals y equals, not function notation. So dy dt will be the derivative of natural log of t. Remember that's 1 over t. And dx dt, the derivative of t cubed plus 1 is 3t squared. So we can put those in here. Dy dt is 1 over t divided by dx dt is 3t squared. And then usually this would be simplified. So again, we have 1 over t. And then divided by 3t squared is the same as multiplying by the reciprocal, which is 1 over 3t squared. So that would give you 1 over 3t cubed would be what dy dx equals. Which again tells you the slope of the tangent line, which leads us right into part B, which says write an equation of the line tangent at the point determined by, so it doesn't give you the point, by t equals 1. So remember, to get the slope tangent line, there's two things we need: the point of tangency and the slope. And the slope, remember, comes from the derivative, which we just found it. So the first thing we can do to find the slope of the tangent line is substitute in this case, notice it's in terms of t, so we can substitute in t equals 1 into that. And we'll get 1 over 3 times 1 squared gives us 1/3. Okay, so there's the slope of the tangent line. And this time to get the point of tangency, that's where we have to go back to our original equation. So the x coordinate is given by t cubed plus 1, so that would be 1 cubed plus 1. That would be 1 plus 1 is 2. And then y is equal to natural log of t, so that would be the natural log of 1. And remember the same, e to what power gives you 1, which is 0. Natural log of 1 is 0. So our point of tangency, x is 2, y is 0, is 2, 0. And then we write the tangent line using x and y, just like we normally would. So our tangent line would be y minus 0, or just y equals, since the y equals 0. The slope we found is 1/3. Times x minus the x coordinate is 2. Alright, now part C says find the second derivative in terms of t. So remember, for our second derivative, the formula we just looked at earlier, we still take the derivative of the first derivative with respect to t, so it's because it's in terms of t here, so it'd be d over dt of our first derivative, dy dx, just like we normally would. But the thing that's different about the parametric ones, that's not going to give us our final answer. We have to divide by dx dt. And again, in order to get those t's to cancel out. So what we're doing is taking the derivative of the first derivative, which we already found was 1 over 3t squared. But to make it easier so that we don't have to use the quotient rule on 1 over 3t cubed here. So we don't have to use the quotient rule on that. It's easier if you rewrite it as 1/3 and use your negative exponents t to the negative 3. And then divided by dx dt, remember we already figured out was 3t squared right here. So then we take the derivative of this one using the power rule now. The negative 3 times 1/3, that just gives you negative 1. The 3's reduced out. Subtract 1 from the exponent, so t to the negative 4. divided by 3t squared, or dxt, and then just simplify it. Notice here, we can just bring the t to the negative fourth to the denominator. So we have negative 1 over 3t squared, and then t to the fourth, which you can combine by multiplying and adding the exponents. So we get our final answer for the second derivative in terms of t again will be negative 1 over 3t to the 6th. All right, let's take a look at one more on this one. This next one says write but do not evaluate. So again, we're just setting it up, but not working it out. An interval expression, it gives the total distance traveled by the particle during the time interval 2 to 5. So again, for distance traveled, total distance traveled, we're just integrating speed, in this case on the interval from 2 to 5. So the integral from 2 to 5. And then remember for parametric ones, because it comes from the quadratic formula, the Pythagorean theorem, it's the square root of dxdt squared plus dy dt squared. And we already figured those out. Remember up here, dxdt was 3t squared. So it'd be 3t squared squared plus dy dt we figured out was 1 over t. So that also gets squared. And then don't forget times dt. T is our variable. And since it said write but do not evaluate, we can just set it up like that. All right, let's take a look at another problem. This one says for time t is greater than or equal to 0, the position of a particle moving in the xy plane is given by the parametric equations x of t and y of t. So notice here they're using the function notation. Instead of just x equals, instead of y equals, it's x of t, y of t. But the notation is different, but the process and the formulas still are the same. So this one says find the velocity vector of the particle in terms of t. So vectors we write like this, and velocity, here's position. Just in general, would be x prime of t, comma, y prime of t. Or it'd be x dt, dy dt if we had the other notation. And here it says in terms of t, so we're not substituting a specific time. So we just take the derivative of each, so derivative of dx dt, you can see it would be 3t squared minus 6t. And the derivative of y is 4 minus 2t. So there's our velocity vector. Now, if we substitute a specific time, we can figure out what the horizontal velocity is using x prime of t, and figure out what the vertical velocity is at that time using y prime of t. And the acceleration vector, that is the second order position, so we could write it as x double prime of t, and then comma the horizontal component of acceleration, y double prime of t. So we already found the velocity vector, so we have to take the derivative again. So the derivative of 3t squared minus 6t is 6t minus 6. The horizontal component of acceleration, and the derivative of 4 minus 2t is just negative 2. So in this case, the vertical acceleration is a constant of negative 2. Now, part C says find the point xy which the particle is at rest. So at rest, again, means it's not moving. So what's different about this, normally you would just set velocity equal to 0 if it was a one-dimensional problem with velocity. But here, there's two components of velocity. So it still means at rest always means the velocity is 0. But our velocity vector, there's two components. So both of these have to be equal to 0. X prime of t has to equal 0, and y prime of t has to equal 0. So it's at 3t squared minus 6t equal to 0, and 4 minus 2t equal to 0. And then we can solve this one by factoring. We can factor out the 3t, and you get t minus 2. So we get times 0 and 2. So that's when the particle's at rest in terms of its horizontal velocity. It's not moving. And when you solve this one, you can factor out the 2, or you could isolate the t either way, and you get t equals 2. So in order for the particle to ever be at rest, there has to be a time that these two have in common, where both the horizontal velocity is 0 and the vertical velocity, component velocity is 0. In this case, there is, not at time 0, but at time 2. So that would be the one time the particle is at rest. However, that's not what it asked for. It didn't say at what time the particle is at rest. It said find the point. In other words, where is that particle when it's at rest? So we know the time, so now we have to take that and go back to our original equation to figure out what the x and y coordinates are. So x of 2 would be 2 cubed minus 3 times 2 squared. Well, that would give you 2 cubed is 8 minus 2 squared is 4 times 3, 12, gives you negative 4. So that's the x coordinate of the particle when it's at rest. And y of 2 would be 4 times 2 minus 2 squared. That would give you 8 minus 4, which is positive 4. Just a coincidence they happen to be opposites here. So those are the coordinates of the point. That's where the point is actually at when it's at rest, at time 2. So it'd be negative 4, 4. That's what it's actually asking for as your final answer on this. All right, let's take a look at a few more questions on this same problem. So the next one says find the speed of the particle at time 3. So again, remember speed because it comes from the Pythagorean theorem. So the square root of dx dt squared plus dy dt squared. But in this case, we have x prime of t and y prime of t, and it's a specific time we're plugging in. 3. So notice on the total distance formula we did back here, you don't plug in a specific time. You just put the general formulas here and there. However, on this one, if it said speed in terms of t, then we wouldn't. But here, it actually is to put in a specific time. So this would actually be x prime of 3 squared plus y prime of 3 squared. And that'll give us what the speed is equal to. So x prime of 3, if we hadn't already found it, we'd have to find x prime of t. But remember, we already found it back in part A. That was our two components of our velocity vector. So that was 3t squared minus 6t. So that'd be 3 squared minus 6 times 3. Well, that would be 3 squared is 9 times 3 is 27. Minus 18 gives you 9. So this is going to be the square root of 9 squared. X prime of 3 is 9. Plus y prime of 3. Well, again, that's the vertical component of velocity. We already found y prime of t here was 4 minus 2t. So that'd be 4 minus 2 times 3. Gives you 4 minus 6, which is negative 2. So this would be negative 2 squared. So, in terms of the direction it's moving, it didn't ask us here, but so you understand what the difference between having a positive and a negative for your velocity components. Since x is the horizontal velocity, the 9 means it's moving to the right horizontally, and the negative on the y prime of 3 means at time 3 it's moving down. So it's moving to the right and down at that in that direction overall. So in this case, we're trying to figure out, well, as it's moving in that direction, how fast is it going? So then we can simplify this. 9 squared is 81, plus negative 2 squared is 4, gives you the square root of 85, which I don't believe simplifies any further than that, because 5, I think, goes into that 17 times, and 9 or 17 are both prime numbers, so that doesn't, there's no perfect squares that we can pull out of there, so it'll just be square root of 85. All right, the next one says find the time or times t, if any, when the tangent line tangent to the path of the particle is horizontal. So remember, with horizontal tangent lines, that's when the derivative dy dx is equal to 0. So, or explain why that exists. Okay. So that's when the remember, a horizontal tangent line looks like this. So we know the slope is 0. And there we would need the overall derivative, which we haven't used yet in this problem. Remember, on these problems, dy dx equals dy dt, which in this case is y prime of t, the same thing as dy dt, over dx dt, which is the same as x prime of t. So we already figured those out. Those are our two components for velocity, remember? So y prime of t was 4 minus 2t. And x prime of t was 3t squared minus 6t. And so for this one, we want to make the derivative 0, so that's where the numerator is 0. So if we set that equal to 0, you can see we already kind of did that, if you remember earlier. Factor out of 2, you get 2 minus t. So we get at time 2. It looks like we have a horizontal tangent line. However, I'm not going to circle the answer yet, because I remember something from a previous part of the problem we did here. Okay? So it looks like at time 2, we got a horizontal tangent line. Well, let's look at the next part, and then we'll see how that impacts our answer for part E. So this one says find the time or times, if any, which the tangent line tangent, same thing as tangent line, e to the path of the particle is vertical. So remember, a vertical tangent line means dy dx is undefined. This tangent line looks like this, so the slope is undefined for a vertical line. So then you would set the denominator right here equal to 0. Again, you might have a sense of deja vu here, because we already did set this equal to 0. When you set factor out the 3t, we get two different times t equals 0 from the 3t and t equals 2. So the reason why I didn't circle the answer from part E yet is, remember at time 2, that was when we were supposed to have a horizontal tangent line. And now we're saying at time 2 there's a vertical tangent line, and that's actually neither. It can't be both. That means both the numerator and denominator are 0, which is indeterminate. So we don't have a horizontal or a vertical tangent line. because it occurs on both of them. So horizontal tangent line just has to make only the numerator 0 to make the denominator 0, and the vertical tangent line has to make only the denominator 0. So notice that was our only possibility for the horizontal one, and 2 doesn't work. So that means this one has no horizontal tangent lines. So you can say, explain why none exists. You can say something like there are no horizontal tangent lines, since all you have to say is what we were looking for is the derivative dy dx equals 0. And the only time that might have made it 0 was 2, but that doesn't because it's 0 over 0, which is indeterminate, not 0. So we can say since dy dx does not equal 0, it never does those. So it never has a horizontal tangent line. We took the half of this problem. But for the vertical ones, even though we crossed out time 2, that wasn't the only time. Remember it said time can be greater than or equal to 0 here. So at time 0, there actually is a vertical tangent line. That makes the denominator 0, but not the numerator 0. Notice if you plug in 0 here in the numerator, you just get 4. So it'd be 4 over 0, which is undefined, does make it a vertical tangent line. All right, and finally, this one again says write but do not evaluate. An integral expression that gives the length of a path. Okay, so the wording's a little bit different here. But the length of the path on this parametric curves, that's really just another way of saying the total distance traveled, right? Because the length of the path, how long the path is, that's how far the particle traveled. So it's worded a different way, but it really means the exact same thing when you see that word on these parametric ones. Okay. All right, so described by x of t and y of t from 0 to 2. So it would be the integral from 0 to 2, square root of the xct squared, which remember we figured out was the same as x prime of t. That's 3t squared minus 6t. And that's squared. Plus dy dt squared, the same as y prime of t, which we had here was 4 minus 2t. Squared, and then, don't forget our variable here is t, so it'd be times dt. And again, I just said write but do not evaluate. So that would give us the total distance traveled, which is the same as the length of the path. And that concludes the notes for AP Calculus on the topic of parametric formulas without the graphing calculator.